Lesson 1.3, Continuity and Behavior and Limits. For today's lesson, our learning target for this part is focused on continuity. That at the end of this lesson, you should be able to identify the type of continuity of a function given at any point. So we have continuous functions, and a function is said to be continuous if there are no breaks, holes, or gaps in the graph. The graph can be traced without lifting your pencil, and it approaches the same value from the left and right side. This last part of this is something that you'll focus a little bit more on when you get to calculus. If you follow your textbook, it follows this approach primarily, and that's not what we do at this course level. It's what you'll look at a little bit more deeply in calculus. So don't pay attention to that part of the textbook because it can get a little confusing. All right, so most of the functions that we've looked at and studied in Algebra 1 and Algebra 2, linear functions, quadratics, cubics, are continuous, right? If you trace them with your pencil, you're going to be tracing without lifting your pencil. There are no breaks, holes, or gaps in the graphs. Now, some of the functions that we studied did have them. Exponential functions, right? They had a horizontal asymptote. We're not really studying exponential functions in this unit right now, so you don't have to worry about that till later. And logarithmic functions, right? That's the inverse of an exponential. They had a vertical asymptote. So again, we're not studying logarithmic right now. We'll reference that later in a later chapter. But the functions that we are working with right now that tend to have interruptions that make the graph non-continuous or discontinuous are rational functions and piecewise functions. So really there's two questions, at least in this unit. There are other types of functions that have interruptions in the graph, but for what we're studying, you're going to ask yourself two questions. And if your answer is no to both of these questions, then it's probably a continuous function. So the first question is it a rational function? Right? That's where we've got horizontal asymptotes possibly, and possibly vertical asymptotes. So if it's a rational function, then it's not continuous. But if your answer is no, nope, there's no denominator with an x in it, then you're good so far. You have to go to the second question. The second question is it a piecewise function? And if it's piecewise, then it's piecewise and most likely has an interruption in the graph, a break, a hole, or a gap. Some piecewise don't, but for the most part they do. So if your answer is no to both of these questions, then you can rest assured that, at least for this unit, it's a continuous function. Next, we're going to look at types of discontinuous functions. The three types of discontinuous functions are a function that has infinite discontinuity, we'll talk about what that is in a second, jump discontinuity, or removable discontinuity. Basically, a discontinuous function is a function that is not continuous due to a break, a hole, a gap, an asymptote, etc. So a function with infinite discontinuity comes from vertical asymptotes. So if you're looking at the graph or the equation and you know that a function has a vertical asymptote, then it will definitely be a discontinuous function. It will have an infinite discontinuity. So if our vertical asymptote is x equals a number, then where you see that number is going to be the asymptote, and it'll be the infinite discontinuity. So let's look at an example. We have the function f of x equals 1 over x minus 1. Well, if I graph this, right, that is a hyperbola, but it is shifted to the right one. So instead of the y-axis being the vertical asymptote, it's here, and it's still the x-axis is the horizontal asymptote. And our graph looks like this. Well, I'm looking at the domain when I'm considering this. I'm looking at the x values, making sure I could follow this without picking my pencil up. And as I follow this from left to right, it's going to go down infinitely. It's never going to cross the line, well, actually not 0. It's never going to cross the line x equals 1, because our restriction is that x cannot equal 1 for this function. In other words, our domain, some of you need practice with that, is negative infinity to 1 joined with 1 to infinity. I didn't ask for the domain here, but you can see there's a break in the domain. And the same thing as I go from the right to the left, it goes up infinitely. It's never going to cross x equals 1. So what we say is that this function has infinite discontinuity at x equals 1. It has infinite discontinuity. So whenever you see a vertical asymptote, you know that there will be infinite discontinuity. Next, we're going to look at jump discontinuity, and this is associated with piecewise functions. So I'm going to draw a function here, and it'll have a couple parts. We'll look at them in a second. And at negative 1, it's going to shoot up and to the right. And then at negative 1, from down here, it's going to shoot this way, like part of a parabola. So I have this piecewise function. Let's say this piece is y equals x plus 3, and this piece is y equals the opposite of x plus 1 squared minus 1. Well, this one has a domain interval from negative infinity up to negative 1. So it's going to have this. X has to be less than negative 1. And this one, which I'm going to fill in up here, is from x is greater than or equal to 1. So when we look at piecewise functions, they always have an associated domain. When I look at this piecewise function, yeah, along here it travels continuously, along here it travels continuously, but from here to here, there's a little gap in the graph because it jumps from there to up here. Doesn't take on a value here, but it does up here. That's called jump discontinuity, where you have to jump to get to the other piece of the graph. So I'm going to look at these inequalities when I look at a piecewise function, and sometimes there's multiple, and I'm going to look at where they break. This one only breaks at 1 point, and that should have been a negative 1. So since it only breaks at 1 point, that's the one I need to be concerned about. If I put negative 1 into this function, into both of these functions, so I have negative 1 plus 3, and I put negative 1 into the other function, negative 1 plus 1 squared minus 1. When I put it into the top function, I get 2 as an output. When I put it into the bottom function, I get 0, minus 1, negative 1. So the fact that I get two different answers, or two different heights on the graph, is a symbol that it is discontinuous at this value of x. So it's discontinuous at x equals negative 1, and because they jump to different outputs, we would say that this is jump discontinuity at x equals negative 1. I want to go back for a quick second to point out that when we're talking about continuous functions, what we've said right here, that it can be traced without lifting your pencil, that there are no breaks, holes, or gaps, is true. If we're talking about a point being continuous, is the function continuous at a point or is it discontinuous? Then the test for point continuity we're going to write down at the bottom of our page. So at the bottom of the page, and we'll come back to the other one in a second, it says point of discontinuity. So basically, if you say x equals c, and you do f of c, and if you get a number, and only one number, and it's a real number, you get a real number, then it's continuous at that point. But if you do f of c, and like we just saw in our piecewise function, there are two parts of the function and we evaluate it in both and we get different numbers, then we have jump discontinuity. Or if we evaluate it and we get something that's undefined, then most likely that's going to be infinite discontinuity. So when we talk about point of discontinuity, I'm actually calling it point of continuity. If f of that number, if you plug that number into the function and you get a real output, and there's no like jumps or gaps in the graph of it, then it is continuous at that point. There's a more technical rule that we use in calculus. We're not there, so don't worry about what it says in your book. Next, we look at removable discontinuity. So I'm going to have to erase a little bit on here for you to see that. Removable discontinuity is what we call it when we have a hole in a graph. So it actually comes from a rational function, and I'm going to give you this rational function right here as an example. So removable continuity comes from a hole. So there we have it. Infinite discontinuity comes from a vertical asymptote. Jump discontinuity comes when we have a piecewise function and a jump in the graph. And removable comes when we have a hole. Well, here's my function. F of x equals x squared minus 1 over x minus 1. Well, if you factor the numerator, x minus 1, x plus 1, you can see that the x minus 1 is going to cancel out, creating a hole. So rather than, if you just looked at the denominator, you would have thought it was a vertical asymptote, but when you factor the numerator and see that the factors cancel, it's no longer a vertical asymptote, it's a hole. So when you graph the remaining function, x plus 1, so I start at 1 and I go up 1 over 1 and get my little graph going here, we have this function. However, where x minus 1 equals 0, there's not a hole, so x can't equal 1. I mean, it's not a vertical asymptote, it's a hole there, where x equals 1 for the factor that cancels out. So there's 1, we have a hole there on the graph, okay? And so that would be said to have removable discontinuity. We would say that this graph has removable discontinuity at x equals 1. It is a restriction on the domain, meaning the function is discontinuous. Again, the key point, infinite discontinuity is for when you have a vertical asymptote. Jump discontinuity is when you have piecewise functions, and removable discontinuity is when you have a rational function that has a hole. Please go to the next video as part of this lesson. Actually, we're going to do it right on this video because it's only 2 examples real quick. Determine whether f of x, 2x squared minus 3x equals, or minus 1, is continuous at x equals 2. Well, we look at the type of function and we see that it's a quadratic, and so we know quadratics are continuous functions. They have a domain from negative infinity to positive infinity, or a domain of all real numbers. So there's no gaps or vertical asymptotes or jumps that would cause the graph to be discontinuous. But to prove this, at least the test that we're running, is plugging the number in and showing that we get a real number output. So f of 2 is 2 times 2 squared minus 3 times 2 minus 1. So that's 4 times 2 is 8, minus 6 minus 1, 2 minus 1 is 1. Since we get a real number output, this is good. It's continuous at x equals 2. So there's the evidence that you'll have to show on your next assessment. Hey, I plugged the number in and got a real number answer, and then the statement that it's continuous at x equals 2. Letter B, determine whether f of x, and this was a piecewise function, is continuous at x equals 0. Now, if I were just evaluating it at 0, I would just plug it into this function because of the equality. Because I want to know whether it has a jump or not, I have to, because there's the 0, I have to evaluate it at both places.